Hi, welcome to my talk on oblivious online vector balancing. I'm Mitab Sani, and this is joint work with Ryan Allweiss from Princeton and Yang P. Liu at Stanford. So we'll be discussing oblivious online vector balancing. So probably one of the most famous conjectures in discrepancy theory is the Komos conjecture. So the Komos conjecture states that for vectors v1 through vt in Rn, each having Euclidean norm bounded by 1, there exists a signing epsilon 1 through epsilon t such that the sign sum of epsilon I vi has L infinity norm bounded by an absolute constant. Unfortunately, the Komos conjecture is still open. The current best known bound is of the order of square root of log n, and this is due to Banashik in 1998. However, this original proof was not algorithmic. This has been made algorithmic by subsequent work of Bunsell, Dedouche, Gard, and Bunsell, Dedouche, Gard, Levet. And algorithmic discrepancy theory in general has been an active field. Two quite famous papers are by Bunsell and Levitt-Mecca, which made Spencer's 6 standard deviation suffice result effective, and has numerous applications, for instance, to randomized controlled trials and online NB minimization algorithms. The problem we'll be focusing on is online vector balancing. So in online vector balancing, instead of being presented with the vectors v1 through vt ahead of time, you're presented the vectors one at a time. So you're given v1, you assign a sign epsilon 1, and then you're presented the vector v2. And the goal is to maintain the L infinity norm of each of the partial sums being as small as possible. So you look at the maximum over all the partial sums of the L infinity norm, and we call that the discrepancy. For example, consider you're given the vector minus 1, 1, 1, minus 1. You assign it the sign 1. Now you have a partial sum of minus 1, 1, minus 1. Only after assigning the sign, you're given the second vector v2. Let's say it's minus 1, minus 1, minus 1, 1. You assign the sign 1. Now your partial sum is minus 2, 0, 0, 0. Now you have discrepancy 2. So you can continue on in this example. And it turns out, so if you pick your signs correctly, you can maintain a discrepancy of at most 2. I think that's optimal here. But if you assign signs all plus 1, well, then you would have the first coordinate being minus 5, and that would make a discrepancy of 5. So you need to be careful in how you choose your signs. There turns out to be numerous different models for online vector balancing. The sort of easiest model to understand is the stochastic model. So here vectors vi come from some fixed distribution p, and this distribution p is known to the algorithm beforehand. So in some sense, even though you don't know your particular vector, you know your vectors are coming uniformly at random from some fixed distribution. The hardest possible model is, let's say, the adversarial model. So after you've made your choice for the ith vector, the adversary then looks at where you are and then is like, okay, I'm going to feed you this vector. Well, it turns out in this case, online vector balancing is not a very interesting problem. The reason is the adversary can simply choose a vector which is orthogonal to your current partial sum. And this is unfortunate because this always increases your, let's say, Euclidean norm. And if you do it correctly, well, okay, this turns out to be not such an interesting problem. So the sweet spot, sort of the hardest model, which is interesting, is the oblivious model. Here, the vectors are decided beforehand. So vectors v1 through vt are fixed by an adversary beforehand, and they do not change based on the randomness used by the algorithm. However, you're not given all these vectors beforehand. They're fed to you one by one. And so there's an obvious relationship between these models in that the adaptive model is harder than the oblivious model is harder than stochastic, and stochastic is harder than uniform. And if you chase through carefully what I told you on the previous slide, turns out there's a sharp upper and lower bound in the adaptive model of square root of t. So that turns out not to be so interesting. However, there has been significant work in the stochastic and uniform setting. So by uniform, I mean here that you're assigned vectors vi, which are uniform on the sphere. And due to results of Bunsell and Spencer, you can get an upper bound of O of log t. So this is just a logarithmic in the number of vectors you have. So it's quite a good bound. And the similar sort of logarithmic in t behavior was obtained by Bunsell, Jiang, Singla, and Singha. They gave an upper bound of n to the 3 halves log t. And Note that although the stochastic and uniform models, they have counterparts in the offline vector balancing problem, the oblivious model actually strictly generalizes the standard offline vector balancing, e.g. the setup for the Cohn-Losch conjecture. And our main results are new strong bounds on the oblivious online vector balancing model. In particular, the previous best known bound is sort of a trivial square root of t. We give a logarithmic bound. So we can prove that there's an upper bound of the oblivious setting of log nt. I should note concurrently there was log nt to the fourth bounds obtained in the stochastic model. So this improves on this n to the 3/2 dependence in the stochastic known previously. However, our results imply this for free because the oblivious model strictly generalizes the stochastic model. So let's give some brief intuition for the algorithm. So it turns out this sort of lower bound coming from your adversary simply assigning you an orthogonal vector forces the algorithm to be randomized in order to avoid the square root t algorithm. So we'll be discussing randomized algorithms. Furthermore, previous analysis of the Cohn-Losch conjecture, they were all based on sub-Gaussianity. And so in particular, the algorithms are always rotationally invariant. And that's a property that's sort of natural to maintain. And finally, given that this is an online problem, sort of the only two pieces of data which should matter are your current partial sum and the next input vector. So in particular, if your current partial sum is v and your next vector is w, then it should only depend on that. And in fact, we even make the simplification that it's only going to depend on the inner product of v and w. And so the probability you assign -1 and 1 should be some function of this. Turns out the algorithm is basically the simplest thing you can do under these constraints. So your initial point is 0, and you set some constant, which is going to be log nt over delta, some logarithmic constant. Now, at every time step, what you do is you say, okay, well, if my inner product of the next vector is too large or my L infinity is already large, well, I have to fail. Otherwise, what you do is you take pi to be 1/2 minus the inner product of your current partial sum and your new vector and divide it by 2c. And you assign the sign 1 with probability pi and the sign -1 with the remaining probability. Now, why is there a minus sign in front of the inner product? Well, if your inner product is positive, then assigning the positive sign would increase your length, say. So it makes sense to sort of avoid doing that. So you want to assign less probability to that possibility. And so that's why there's a negative sign. And then wi is wi minus 1 plus epsilon I vi. So you maintain a partial sum. You assign a sign, which is a random Bernoulli with, which is a linear function of the inner product. And the algorithm fails if the inner product is too large or the probability is outside of 0 and 1. And the main theorem is this works. So this gives a log nt over delta L infinity norm with probability 1 minus delta. So the steps in the analysis, so let wi be the partial sum. So we consider the distribution of wi at every time step. And okay, the algorithm might have failed before this. You can either keep the point where it turns out to be convenient to move this like mass to 0 or use something slightly different, but for now, just consider the mass move to 0. So we show two things. First, we show that conditional on the algorithm not having failed, you can bound the covariance of this vector wi, this random vector wi, and then you convert this into a concentration inequality. So we need to convert this covariance matrix bound into a high probability bound. And the concentration bound is necessary to ensure that the algorithm doesn't fail, and so that you can bound the L infinity every step. So in particular, the algorithm, if it runs for all t time steps, sort of has to give a good answer, but you don't know that the algorithm actually reaches the end, and that's the reason you need a concentration bound. And we need a pretty good concentration bound because we're aiming for logarithmic bounds. So first, let's do the covariance matrix bound. So let mi be the covariance matrix of wi. Then mi turns out to be at most c times the identity. There's a slight lie here, but I'll explain why. So recall that epsilon I, so you choose a sign 1 with probability 1/2 minus the inner product over 2c and -1 otherwise. So let Mi be the expectation of Wi transpose, in particular the covariance. And Wi plus 1 is Wi plus epsilon I Vi. So then the expectation of Wi plus 1 transpose given Wi is equal to Wi transpose plus Vi transpose minus Wi transpose Vi transpose over C minus Vi transpose Wi transpose over C. So this is just applying the previous formula plus expanding. And it turns out that if you just do some basic inequalities, so in particular now you re-average over Wi, you can prove that Mi plus 1 is upper bounded by C times I, given that Mi is bounded by C times I. And so that completes the proof of the covariance bound. So this is just follow your nose. And the reason this is a slight lie is, well, if the algorithm has failed, this statement that Wi plus 1 equals Wi plus epsilon I Vi is a slight lie, but okay, this can be repaired. So the key idea is to sort of convert this like concentration bound into a stronger bound. And so we say a random variable W on Rn is a spread of a random variable X on Rn if there exists a coupling between X and Y such that the expectation of Y given X equals X. So a more intuitive notion is that Y can be sampled from X by first sampling X and then adding some mean zero noise, which is conditional on Y. So it can be different mean zero noise based on what you sampled for X, but it's always mean zero. And this is sort of, you're sort of spreading the distribution from X to get to Y. This univariate notion, this univariate definition, the univariate notion of this definition appears in the mathematical economics literature under the names mean preserving spread and is closely related to second order stochastic dominance. So it turns out spreading satisfies several useful and intuitive properties. So first, it satisfies linearity. So if Y is the spread of X, then for any linear transformation M, which is fixed independent of Y and X, My is the spread of X. Similarly, it's transitive. So if Z is the spread of Y is the spread of X, then Z is the spread of X. Then convexity. So let Y be a spread of X. Then for any convex function phi from Rn to R, we have that the expectation of X given X of phi of X. So little x is sampled from capital X. The expectation of that is less than phi of Y, where little y is sampled from capital Y. So this is just by Jensen's inequality. And finally, you have spreading for univariate random variables which are bounded. So let X be a real valued random variable with expectation of X equal to 0 and the absolute value of X bounded by C. Then you're spread by the Gaussian, which is N0 of pi C squared over 2. So for the first example of spreading, let's consider spreading between Gaussians. So if you have two PSD matrices A and B, where A is less than B in the loner order, then N0A is a spread of N0B. So, and the proof here is one line. Notice that you can sample N0B by first sampling N0A and then adding independent N0B minus A. And the last thing is well defined because B minus A is positive semi-definite. And note, this is sort of a very special case. The mean zero random variable I add is sort of independent of what I sampled for N0A. And in general, it can differ based on what you sample for the first random variable. And this is critical for our analysis. So now the main lemma in our paper is to prove that N0 of 2 pi C times I is a spread of the distribution Wi for all times I for all times. And given the fact that we prove that follows from Jensen regarding convexity, the proof is actually pretty immediate. So suppose you have the lemma. Then all we need to do is verify that the algorithm doesn't fail with a high probability. So in particular, we need to verify that the inner product with the new vector and our current L infinity is bounded. And this follows because essentially by the definition of spreading and using the function phi of x, which is x above x dot u squared over 8 pi c, so this is some convex function, you can prove that Wi is order C sub Gaussian. And this sort of immediately gives the desired concentration equality. So this is a rather standard step. I'm sort of hiding all the details. You need to prove that you're spread by this Gaussian at all times. And during the last few slides, I sort of want to give a high level overview and actually even give most of the details. So what I'm going to prove is that n0 of 2 pi ci is the spread of the distribution wi at all times. So intuitively, this is sort of replacing the earlier covariance bound with being spread by a Gaussian, which is a much, much stronger bound. So recall that epsilon I is 1 with probability 1/2 minus wi vi over 2c and minus 1 probability 1 minus pi. And then you know that wi plus 1 equals wi plus epsilon I vi. And note that the expectation of wi plus 1 given wi is I minus c inverse vi transpose wi. This just follows by direct computation. So this is the expectation of wi plus 1 given wi. But you're not always what your expectation is. You sort of drift around that. And the way to capture this is through the quantity r of wi vi, which is 1 plus c inverse the inner product of wi vi with probability pi, and minus 1 plus c inverse wi vi with probability 1 minus pi. So it turns out the reason you define this is wi plus 1 is I minus c inverse vi transpose times wi plus r of wi vi times vi. So the first term corresponds to your expectation of wi plus 1 given wi. The second term is sort of your variance around that expectation. Now note that if the algorithm hasn't failed, wi vi by definition is going to have inner product MOC. So r is a bounded random variable. In particular, it's always bounded by 2. And furthermore, you can sort of check that by definition, it's going to be mean 0. So it's mean 0 and is always supported on minus 2, 2. Well, then we have this fact that you can spread this to some Gaussian. So that term you can spread to some Gaussian. Furthermore, using induction, you know that wi is spread by n0 2 pi ci. Now you use linearity. So we wanted to look at this fixed matrix I minus c inverse vi transpose times wi. So that random variable is spread by I minus c inverse vi transpose times the normal of n0 I minus c inverse vi transpose times 2 pi ci times I minus c inverse vi transpose. This corresponds to the first term. The second term coming from the r of wi vi is spread by n0 2 pi vi transpose. It turns out you can add these due to some appropriate constraints. It turns out the distribution of n0, this ugly expression, is the spread of wi plus 1. Now you use it turns out the exact same inequality that I told you for the covariance bounding. Turns out that this ugly matrix is always bounded by 2 pi c times I. And with that, you've basically proved by induction that you're spread by the same Gaussian at all times. And that's it. So this algorithm achieves logarithmic bounds for the online Kolmos problem against oblivious adversaries, and furthermore, it runs at input sparsity time. And roughly, the algorithm chooses random signs with a probability that's a linear function of your current partial sum, of the inner product of your current partial sum and the next vector vi. And the analysis is based on the concept of spreading and bounds on covariance. And the main open question left by this work is, can you achieve a similar algorithm which gives you a log NT bound? And this would turn out to be basically sharp in the online setting and would match bounds known in the offline setting. And recall that the online Kolmos problem against oblivious adversaries strictly generalizes the offline Kolmos problem. And in recent work with Ashwin Sa and Yang Liu, we can achieve an O of square root of log NT bound, but there's a slight defect. We need a 2 signing. So instead of adding the vector plus minus vi, we might need to add 2 times your vector vi. And this is in the online setting and runs essentially in input sparsity time as well. So thank you. This paper is available on the archive. Oh, I should also mention the final paper gives an alternate proof of the log NT bound in this result. But this paper is available under the title Discrepancy Minimization via Self-Balancing Walk. And thank you for your attention.